By all means, a critical value or a cutoff is just a score. There is a difference between an observation and a score. The score is a standardized version. We will not get into too much detail. Critical values, also known as cutoffs, are simply scores. I mentioned a whole bunch of distributions last time: Z, T, F, chi-squared. Every single distribution will have a score that you can find in order to come up with some conclusion. Okay, I'm going to pick the simplest case. We can look at the other ones as we get more. The simplest one is normal bell curve. Do we remember? Okay. Case 1. Case 2. Case 3. You might wonder, they all look the same kind of. What does it mean by case 1, 2, 3? Explain in a second. I take here 1, 2, 3. Then I wrote the first step, the definition of the test, and mentioned that you cannot have an equal sign in the alternative. Do we remember? We test for whether we have a greater than, increase in something, decrease in something, or not equal to something. So you never put an equal sign in the alternative. The case that we did last time, Alyssa, I believe, gave us an average time spent on TikTok. Right? The claim that we tested for is greater than something, and in order to verify, I drew the reference distribution, which is the null distribution, also known as the comparison distribution. And I said we don't look at a single data point, rather we look at the data distribution. If it has a lot of overlap with the null, we don't reject the null. It's got to go far away from our reference. In the previous problem, did we look on the right-hand side or the left-hand side? Right. So the farther we moved away from the center, which is our reference distribution, we concluded that we need to reject the null. So I've got to move farther and farther in this direction. Good. So, right. I greater than inside. Mentioned, well, we can't arbitrarily pick a value on the right-hand side and say, well, I went far enough, good day, significant. Science does not work that way. So there has to be a rationale behind picking, that cutoff value. Moving to the right, that is my cutoff point. Since we are dealing with bell curves, I will give it a letter Z. When you did your previous star plots, first course of it, you might have seen, let's go with mean 10, standard deviation 2, mean 100, standard deviation 7. But here, when we're dealing with scores, the mean is always 0. Standard deviation is 1. What Catherine mentioned. 1 standard deviation away from the center, 2 standard deviations, 3 standard deviations. Good so far. Okay. Let's deal with this first, and then we can move on to those two. The area under the curve would correspond to, let's see, who took statistics last semester, either summer or spring, 2023. You can't lie to me, I can pull up your schedule and look it up, so be honest. Carrots, okay, the area under the curve. What does it correspond to? I know you can do it because you're the only person who brought up binomial last time.
The area.
What are you finding if you find the area under the curve?
Whether or not project.
Without even getting to hypothesis testing, what quantity does that correspond to that shaded area? Caroline, did you have an answer?
The probability.
Louder.
Probability.
Very good. It is the probability. So don't forget it. Area, probability. Always. In statistics. It doesn't matter why you draw it, whether you draw it here, there, in the middle, tiny little area somewhere, doesn't matter. Area under the curve is probability. Good? Can't forget it. Very important. This is the crucial part I've mentioned, as if you understand chapter 7 really well, you're set for the rest of the semester. It's just procedure after procedure. Logic is the same, so pay close attention. So we are going to reject if we exceed that value, and we can't arbitrarily pick that value, so we are going to make use of that probability. Good. Well, what should that value be? Do we know what that letter is in Greek? Alpha. So, in social sciences, I've often seen people refer to alpha as P-level. I don't like to do that because it's confusing, because there's another thing called P-value. P-value and P-level are not the same. If you want to avoid confusion, just call it alpha. Alpha is P-value. It is the significance level. Why do we call it the significance level? Well, this is the value that is going to help us either reject or not reject. Okay? Statistical significance or no statistical significance. Hence the significance level. Good. Okay. There is another context. We won't talk about that until we get to chapter 8. So this value shaded area would equal to alpha. The common values for alpha are 0.1, 0.05, and 0.01. let's see if you remember. Caroline gave us that this is a probability, some tiny number. What is the total area under the curve? 1 or 100%. In case you forget, think of a pie chart, right? What is the total percent in a pie chart? 100%. Instead of looking at it as a bell curve, think of it as a tiny sliver of it, some percent. Shade the entire thing, 100%. Good? Okay, that's it. I'll let you pick one. Who wants to pick? Caroline.
0.85, that's not I'm used to.
0.05. What's your name?
Katie,
Casey.
I was gonna say.
0.05. Okay, it's a traditional value. We'll come to you next. A question. 0.05 is the standard value, 5%. So think that it said shade the entire thing 100% of the pie. If this bit is 5%, how much do you have left? 25. Very good. 95%. If that is 1%, what do you have left on that side? 99. If that is 10%, what do you have left on that side? 90. Very good. Okay. I want you to look in your notebook. You took notes. Last time, I said you've got to compute something from the data in order to come to the conclusion, in order to obtain the conclusion. And I believe it was step number 4, where we use data to find something. What is that something that we need to find? The test statistic. Yes? Okay. That is my cutoff. Z score, in this case, easy example. Now, data is going to give us the test statistic. If I am going to reject the norm, conclude that there is significance, where should the test statistic fall? No? No? Yes, it should be somewhere here. So this region shaded right here is called critical or rejection region. The name should be self-explanatory. You're rejecting based on that interval, hence rejection region. Why critical? It's critical in attaining a conclusion. Good. If you Google, oftentimes you may not see a separate real number line. People would simply draw this, come to a conclusion. I personally think that you understand things better if you sort of separate probability part from the test statistic part. Good. So still 0 here. Do we have our calculator? Yes. Let's pick up the calculator. So I'm going to show you how to find the critical value for the first case. I wrote it as number 3, but it is the first one we started. It is on the right hand side of 0. So whatever number that you find has to be positive or negative. Has to be positive. Okay. The dreaded Z table that some of you might have encountered in the previous class. We're not going to do that. We're going to use this. Press second, the blue button, followed by bars, right next to clear. Got a whole bunch of options. Out of those, we are going to pick number 3. INV and norm stands for normal. When you put stuff in the calculator, you always put the area below whatever school that you're looking for. In my case, I've shaded to the right-hand side, and you were all correct for all 3 cases when I asked, if area above is 0.1, what is below? 0.1, this side, 0.9, 1 minus 35. So if I put 0.9, I will get 1.28. Good. Let's say by some accident you ended up putting 0.1. Let's say you didn't think at that moment and you ended up putting 0.1. Of course, you can't correct yourself. You look at that diagram or picture that you drew, it is to the right of 0, but you're getting a negative value. But if you compare those two, in magnitude, they are the same. So it should click, and you simply change the sign. Good. In case you don't recognize it, which is yet another reason why I tell my students to draw that picture. Very important. Are we clear? Go ahead and tell me what number you get if alpha is 0.01. Give it a try. If it is 0.01. Very good. So the next one, 8. 2.328. Thanks, okay. What's your name? Olivia, okay. 2.328, did we get that value? Or 326, good. Okay, so if the test statistic exceeds, say, 1.28, we will reject. 2.326, we will reject. At that level that you chose, I will explain what this is, and then it makes sense as to why we have to paint this level. It's coming in chapter 8. Good so far? Okay. Time to think. Right inside, greater than f(x). Going to go over here. What should the alternative be? In the sense, what should the sign be? Whatever effect that you're measuring, is it an increase in something, decrease in something?
Let's say decrease.
Decrease. So what sign should I put down?
Less than.
Good. On which side should the critical region be? Right hand side, left hand side. Left. We've got to go as far as possible away from 0 towards negative infinity, to have as little of an overlap as possible. So Same logic. You pick alpha. That is the probability area under the curve. You will have a critical value, as that's called. In this case, it will be negative or positive. Negative. I'll put that negative sign so you know the difference. That leaves us with the one in the middle. But before we get there, would you like to give this one a name? Left. Okay. Why should, well, we'll start here. What sign should go in the alternative?
Unequal sign.
A not equal sign, okay. Why should the rejection region be?
Both sides.
Both sides. Why?
Because it's both sides.
So it is not equal to, and I can support that case if this is the center, I know, and if I go too far to the left, not equal to null. Too far to the right, not equal to null. So regardless of the direction, I will reject the null if I went far away. So the rejection region has to be on both sides. Do you agree? So one on this side, one on that side. What is the shape there?
Isn't the alpha like split in two?
Why?
Because it's still the same alpha value, but it's on two different tails.
Very good. The alpha value is the same. Regardless of the test, you picked one alpha. But depending on the test, you either put all of alpha here, all of alpha on that side, or you split it in half. Good. So the area in that case would be alpha over 2. This underlying principle is a recurring theme with every single test that we'll be doing in this semester. So understand, things that would change would be the scenario, the formula for the test statistic, the function that you use in the calculator, the shape of this curve. The content, principle, exactly the same. One more item, and then I'll explain p-value. I want you to name this one first. Middle, naturally, that's what we're going to say. Middle, okay. Left, right, middle, what should it? Riley, I knew middle is going to come. What else? That's it.
Two tails.
Two-tailed, tailed. So left-tailed, right-tailed, two-tailed. These are testing scenarios. When we get to chapter 8, 2, we will see something called the confidence interval. A confidence interval pretty much follows along this. I don't want to discuss it now, we'll save that for chapter 8. But do we understand this better? Good. Don't forget this. Last thing for chapter 7 is p-value, not p-level. Test it down and it will make sense. Yes. Current test. First, let's understand this and then add this important component that will make more sense, or that will make us understand things better. So the probability of observing a test statistic based on whatever conclusion that we have, such as whatever test that we did, or getting bigger than what we just found. Let's say I have a test statistic of 7.82, hypothetically. The one that we did using the calculator that cut off 2 cases, we had 1.2 approximately, and we had 2.3 approximately. With that, those values form the cutoff, and my test statistic is 7 point something, way in here. Yes. So, should I reject the null? Yes or no? Absolutely, I should. So, the probability of observing 7.2 or something bigger than 7.2. Good. Firstly, that is this table. But this in and of itself doesn't make great sense. So, I'm going to add another bit. This bit is important. That condition is important. So, let's say that the null is true, but there is no effect whatsoever. If that is the case, is it possible for us to get a test statistic of 7.2? If the null is true, I'm sort of working backwards. Null is true, I'm supposed to be here. Data gave me 7.2. If you use reverse logic, well, data gave me 7.2. If that is the case, could the null be true? Absolutely not. Yes? So, if this condition is true, and I get a test statistic of 7.2, the p-value is going to be extremely small. If you read that statement, the probability of observing a value of 7.2, if the null is true, is less than 1 in 1,000. It's highly unlikely. Well, now how do I know this? That's experience. I know it's going to be less than 1 in 1,000. Read that sentence. Probability of getting 7.2 if null is true is less than 1 in 8,000. This should simply mean null is not true. Do you see the logic? Read the statement in blue and read the statement in black. Are they equivalent in a sense? Okay, if you read this statement, if you look at it over here, if I say it is true and I get a test statistic of 7.2, the chances of that happening is highly unlikely. Correct. So either this is wrong, or that is wrong, or both of them are wrong. Correct with me? Because the chances of this scenario happening is extremely small. Agreed. So one of them or both of them has to be wrong. But when we started a test, I assumed that the null is true. Correct. So this is my assumption. I'm starting with the reference, with the assumption that the null is true. And I'm getting this. But I'm saying, well, the probability is very small. If you backtrack, that would simply mean whatever assumption that I made cannot be true. Agreed? So I'm starting here, getting this. Statistics is dependent on data. You put weight on data. This entire statement is highly unlikely, is my conclusion. That would mean either what you started with is wrong, or the data is wrong, or both of them are wrong. Yes? So we place weight on data, statistics, evidence. So given the data, looking at this number, only one of them has to be true. This is true. Your assumption is false. In other words, H0 is false. Sophie, did I lift that contradiction away? Does that make sense? Sort of a convoluted way of looking at p-value, but there's an easier way, informal way, and I'll explain that in when I get to type 1, type 2 errors.